Okay, guys. Let's finish up this clicker question. If you were watching, I just have the answer up there. But what is the magnitude of the force F2? All right, I'm going to stop at 33, 35, 35. All right, awesome. Remember, equal and opposite, good application of Newton's third law, that anytime I have an electric force, I'm going to have an action-reaction pair, all right? What do you call Santa's helpers? How do you do a joke? We say, I don't know, what do you call Santa's helpers? Subordinate clauses. Fix this somehow. If we increase one charge to 4q, what is the magnitude of F1? Initially the force is 3 newtons. I increase one of the charges to 4 times its original amount. What is the new force? F1. All right, I'm going to stop at 35. 35. You are amazing. You are awesome. The answer is it is 12, right? Because it's a linear relationship. That's one of my jokes. So, what do you call cheese that doesn't belong to you?
Nacho cheese.
Ah, nacho cheese. All right, the force between two distance is F, between two charges is F. What if you pull those charges apart by a factor of 3? What happens to the force now? Feel free to ask your neighbor, and you're closer now, so you can reach out and touch them. All right, I'm going to stop at 35 again, 35. Okay, E is right. Listen, it's an inverse square relationship. F is K, Q over R squared. So if I increase R by a factor of 2, then that means that, or by a factor of 3 here, then I decrease F by a factor of 9. It's an inverse square. I would expect some questions like that exploring the relationships between those different variables for force, for fields, and for potential, how they're related to one another. You have the equations. It's really just you need to look at the equations, but then think about how they are related, those variables. All right. 2 balls with plus q plus 4q are separated by a distance of 3r. Is it possible to place another charge on the line between them such that the net force is 0? And which of those options? You had a couple of problems on your OpenStack quiz that's related to this, number 3 and 4 at least. I think some others maybe. All right, we'll go to say 40, go to 50. Okay, good. C is right. The best way to approach this is just imagine if I have charges. So if I put a positive charge here, it feels a force due to this charge. I can't really see that, can you? If I put a positive charge here, due to this charge, the force is in this direction. Due to the other charge, the force is in that direction. So it is possible for this charge to have a zero force. By the way, where does it need to be? Here in the middle, to the left of the middle, or to the right of the middle? Hey, y'all are awesome. It needs to be to the left of the middle, further away from this big charge, so that this force is minimized and this force is maximized. Right? Because this one will exert a bigger force if it's the same distance. Right? Imagine a negative charge here. You get the same set of forces. It's just these two vectors are switched. Okay? All right. Remember, R is not the radius, it's the distance separating them. I know we usually use R for radius, but it's a separation, not a radius. Huh? Oh, no. Crazy. Okay, let's stop at 45, 45.
When you see that article where they apparently at Harvard they made hydrogen into a metal,
I did not see that, no.
it's like a Liberty or something, they squeezed it squeezed the molecule or two of the hydrogen, and it was apparently more than the precious acidity originated from metal.
Huh.
I don't know if that was true or not, but apparently.
I don't know. All right, it gets bigger, very good. Because the separation between the charges decreases. All right, which particle has the larger acceleration in this case? Same scenario, which has the larger acceleration? All right, we'll stop at 20. We'll go to 23. 23. All right, B is right. Why does the electron have a bigger acceleration? We just said they have the same force, so it doesn't really jive with me. Why would the electron have a bigger acceleration? The mass, right? Electron is like 1/1000. No, it's more than that. It's a lot smaller than a proton. Is it a million?
I don't know exactly what
It's a heck of a lot smaller than a proton. So, than an electron, rather. Yeah, an electron is a lot smaller than a proton. Where would they meet when you let them go? All right, we'll stop at, say, 25. 25. Awesome. Have I said y'all are awesome today? It's true. All right, so why is it closer to the proton side? Well, the proton, we just said it accelerates at a much slower rate. So it's like electron here, or proton here, electron here. The proton sort of moves like this, but the electron moves like this. And so it meets over there, not in the middle, but closer to the proton. All right, which of these best represents the direction of the net force? That's your 1 through 5, the, A through E. We did one like this. You want to sketch out the vectors for each charge configuration, and then try to figure out which is the sum of those two vectors. All right, we'll stop at 40. Stopping at 40. Okay, good. B is right. Look, my forces look like this. Due to the plus 4q charge, I have a big force in that direction. Due to the plus 2q charge, I have a smaller force in that direction. They're the same distance from the plus q charge, but the 2q charge is smaller, so the force is half of the other. And so the sum of these would be B. That's what y'all put, right? Yeah, so B is the right answer. Oh, what do you call a boomerang that doesn't work? A stick. Okay, you're sitting a certain distance from a point charge, and you measure an electric field. You double your distance, you double your charge. What is the electric field strength now? First of all, you're going to ask yourself, how do I find the electric field due to a point charge? And look back at your equation sheet here, notes or whatever you've forgotten. But remember that the electric field is very similar to force. All right, we'll stop at 55. 55. Okay, D is right. I understand why some of you put E. Let me show you. First, you want to write out your expression. E is KQ over R squared. I am doubling Q, and I'm doubling R, so I get a factor of 2 over 2 squared, which is 4. So I get my electric field is half what it was originally. Red and the blue charge, which of them experiences the greater electric field due to the green charge? All right, let's stop at 42, okay? 42. Just guess if you don't, not sure. Hey, that's pretty good, actually. That's a lot better than I thought you'd do. Listen, I know you sort of think that, well, this is a bigger charge, so it must experience the greater electric field. Remember, the electric field only has one Q in it. E is KQ over R squared. So the electric field here, due to this charge, is the same than it is as it is here. The electric field due to one charge is just due to one charge. It's not an interaction between charges. It's just the field surrounding a charge. So this charge doesn't impact the magnitude of the electric field due to this charge. Now, this charge does have its own electric field, right? And so we have to consider that as well. But as far as we're thinking about the electric field due to the green charge, they're the same at both positions. That was good. All right, which one feels the greater force? The blue, red, or is it the same for both? All right, we'll stop at 25. 25. Okay, good. B is right. It experiences the greater force because remember, F is equal to Q times E. And so the one with the bigger charge, they have the same electric field, but the one with the bigger charge will experience the bigger force. So here you have a 4 coulomb charge. It feels an electrical force of 12 newtons when you put it inside this electric field. If you remove it and put in a 6 coulomb charge, what force will it feel? My shoe is squeezing this way. That bother you? All right, we'll stop at 50. 50. Just 5 more seconds. Guess if you're not sure. Y'all have the answers? Did you get them from somewhere? Because that's rocking, man. Y'all are awesome. Did you have the answers? Like, do you have them somewhere written down? No. All right, so look, you can approach this a couple different ways. You can say, well, this charge is 3 halves that charge, so the force is going to be 3 halves the force. And 3 halves of 12 is 18. Or the easier way, and this is the way I sort of think of it, is if I have 4 coulombs and it has 12 newtons, what must the electric field be? 3, right? And that's probably how most of you thought of it, right? 3 newtons per coulomb. 3 newtons per coulomb with 6 coulombs gives us 18 newtons. So that charge would feel a force of 18 newtons. What are the signs of the charges here? You can see this, it's in your book, but the arrows are going in this direction. All right, let's stop at 30 seconds. 30 seconds. Is there a problem back there? Do I need to come back there? I will. Awesome. Don't forget your electric field lines, how to determine both the ratio of the charges and the sign of the charges. Field lines always come out, thank you, positive charges, and they go into negative charges. Hey, what name does a one-legged lady have? Eileen. I'm glad that none of you ladies are one-legged. And I can tell you many of my one-legged lady jokes.
How many do you have?
I think I might have one more. But you really shouldn't make fun of anybody, even if they're not around. Like, okay? Like, that's what I tell our kids. Right? Y'all agree? I'm not making fun of one-legged women. It's just a joke. We're gonna say, just settle down. All right. Which of these charges has the greater magnitude? arrows are still the same, moving right to left. All right, let's stop at 25. Look at that, y'all are awesome. All right, by how much is it bigger? By what factor? Like, let's say this one is the bigger one. Well, let's say this is 6 coulombs. What is this charge? 12, because it has twice as number of lines. So you'll probably see a question where I just show you a configuration of two charges, and you have to tell me about the signs and or the magnitude of the charges, or the ratio of the charges, or something along those lines. All right. That is the end of chapter 1. Now listen, your exam on Monday. We have an exam on Monday? Well, 1 week from Monday, excuse me. 1 week from Monday is going to cover all of chapter 1, of course, and then definitely chapter 2 up to capacitors. And then we might add on just a tiny little bit of capacitors, because it's good for you, and I love you, and I think that you're awesome. Might add on just a little bit of capacitors, okay? Because it'll make the exam a little bit easier. But we'll see sort of how we're doing next week on Friday. Okie dokie? So let's jump into chapter 2. It's on electrical energy and capacitance. A couple different things we're going to look at this. We're going to see potential. If you study the nervous system, you study potentials, right? You'll talk about your action potential and the what? The graded potential, yes. So that's what this is. It talks about the energy between two different points, the electrical energy between one point and another point. And so we'll see that in just a bit. But first, just a little bit of background. Electrical forces are conservative, just like gravitational forces. And do you recall what that meant when we said that gravitational forces were conservative? What did that mean? They don't lose energy, right? So they conserve energy or they don't lose energy. I like that even better. And we talked about, frictional forces, on the other hand, are non-conservative. That means that as they act on an object, that object loses energy. Non-conservative force. Right? It loses energy because the frictional force takes away energy. Conservative force is path independent as well. Conservative forces include, you remember we talked about how if you go up a mountain, you can go up a couple different ways. You can go up the long way like this, or you can go up the short way. And the conservative force, as it acts, is going to cause the same change in energy. So your gravitational potential energy is going to be exactly the same when you get to the top, whether you take the long route or the short route. But the frictional forces, on the other hand, are different, right? So the frictional forces, if they act over a longer distance, they'll take away more energy. Conservative forces include like field forces. That is gravity, which we've already talked about, and then also electrical forces. And non-conservative forces are contact forces like friction, normal forces, and the like. The work done by conservative forces is path independent. The work done by non-conservative forces is path dependent. That's just what we said. Friction, gravitational forces. Also for conservative forces, the work energy theorem. We had this last time, that if I do work on an object, then I change its energy. That's also true for work for conservative forces. And so if work causes an increase in kinetic energy, then what happens to the potential energy of an object? It's going to decrease, right? So if I have if work causes an increase in the kinetic energy, then we can write the potential energy as negative of the work. All right, that's just if, say, our kinetic energy goes up, then our potential energy goes down, conservation of energy. All right, this applies when the electric field, by the way, is constant. It'll always be constant as far as we're concerned. May I go down from here? All right, so say, for example, we have this particle that moves from A to B. So this is actually a capacitor. It's two metal plates that are set up next to one another. One of the plates is positively charged, one of the plates is negatively charged. The electric field lines run from positive to negative charges. And so if I have a positive charge here, it feels an electric force to the left or the right? To the right, right. So the electric field lines are in the same direction that a positive particle would feel a force. This is a line of force, they also call it. So my positive particle will feel a force that will push it from A to B. Has the electric field, in this case, done positive or negative work on this positive charge? Let's think back. Work was that force times displacement. And we said something last semester about the force and the displacement being in the same direction or the opposite directions. So in this case, is the work done positive or negative? Has it done positive or negative work? It's positive because the force is to the right and the displacement is to the right. So the electric field has done positive work. I'm going to go to blue, guys. The force and the displacement are in the same direction. All right. Has the potential energy of the positive charge increased or decreased? Well, what's happened to the kinetic energy? Right, it has this force acting upon it, so the kinetic energy is increasing. The potential energy here is decreasing. Right, so the potential energy here has decreased. And I can think of this as the kinetic energy has gone up, so the potential energy has gone down. So where has the energy gone? I've done positive work, and the potential energy has decreased. I said it right here. The particle speeds up. It has kinetic energy. It has more kinetic energy. And that's sort of the crux of this, that as I have charges move in an electric field, you can change their kinetic energy. And you can change it very predictably. You can move them however you want to move them. So if the charge has lost potential energy at point B, its kinetic energy must have increased. You know, that's the work energy theorem. Increased the work energy theorem. And then we can calculate the charge's speed at point B. The kinetic energy is equal to the negative of the change in the potential energy, which is equal to 1/2 mv squared. So if I have the amount of work that's being done, then I can also figure out what is the particle speed. Let's try an example. I know that's a lot of stuff to say this, but it's kind of important. And as you move on to graduate school or wherever you go, as you use different instruments, you might be using instruments that use ideas like this, like, you know, a mass spectrometer. We'll see a mass spectrometer later, but a mass spectrometer uses an electric field to accelerate a charged particle to a certain speed. Or the cathode ray tube works similarly, use an electric. No, you don't use cathode ray tubes, but we used to, right? For televisions, the big old televisions, they use an electric field to accelerate electrons to specific speeds. All right, let's try this. I have a proton. It's released at x equals -2 centimeters and an electric field of 1,000 newtons per coulomb. What is its velocity at x equals 8 centimeters? Your reading goes into this quite a bit too. For next week, your reading that's due on Tuesday. So, what I want to do here is my change in kinetic energy is equal to the work that's being done, which is equal to my force times my displacement. All right? Now remember, F is equal to Q times E. So my force then, right here, is equal to Q times E times, I'm going to just rewrite D as delta X here because I used X here. Okay, but D is the same as delta X. All right, and so now I can figure out the change in kinetic energy. I can say that 1/2 mv squared is equal to Q E delta X. And I'm looking for V, so I solve that for V. It's 2Q E delta X, what, over M? The square root of that. Don't try memorizing the formulae, but just remember that our work is force times distance. Right? So you will need to know that. Like you need to think about how this work works. Right? Remember, it's sort of these basic ideas from last semester. Our work is equal to our kinetic energy. That's just the work energy theorem, really. And then I can solve for the specific velocity of discharge as it moves through this this electric field. So let's go and put in some numbers there. So a lot of students get hung up because what they say, the charge isn't there or the mass isn't there. But don't forget, for your basic particles, your proton and your electron, those are all on your equation sheet. So my velocity is equal to the square root of 2. And then you look on your equation sheet and say, the charge of the proton isn't there. Where's the charge of the proton? It's the what? It's the fundamental unit of charge. It's called E, right? So that is the charge of a proton and an electron, that 1.6 times 10 to the minus 19 coulombs. We're going to always use coulombs for our charges. E here was 1,000 newtons per coulomb. And delta X is going from 8 centimeters, or excuse me, from -2 to 8 centimeters. So my delta X then is equal to 8 minus -2, or 10 centimeters. But I don't want to use centimeters, right? I want to use meters. So centimeters and meter, 10 centimeters is, see, there are 100 centimeters in a meter, so 0.1, or I just move that decimal place 2 spots over. So it's 0.1 meters divided by the mass, 1.67, is that right? Times 10 to the minus 27. That's right, isn't it? Yeah. Okay, so that'll give us our speed, and it turns out that speed is 1.4 times 10 to the 5th meters per second. All right? So we're going to move into electric potential difference, but this idea that we can use electric fields to accelerate particles is pretty important. You'll likely see some questions on there dealing with how particles move through electric fields, and then also, can I just calculate the speed of these things? You have a homework question that's similar to this, and you can look at the old test as well. Before we do that, though, I want to watch a video, because as you guys are moving into your various classes that deal with the nervous system, as I said, you'll work with electric potential and electrical energy and potential energy, and you might even touch on electric fields in those classes. Maybe not, probably not. But there are other applications of electric fields in medical sciences and the health sciences. And this is one that there's a guy giving a TED talk where they use electric fields to combat cancer. And so this is, we've all been touched in some way with family or our friends that have had cancer. So it could be very exciting to see what comes from this. But let's watch this. They talk about how they use electric fields, localized electric fields, to cure cancer. It's all very early though. I really do think that this class, compared to last semester's class, I mean, they're both useful for you, especially if you guys going on to medical school, because you'll see it on the MCAT, and you'll see some of it in medical school. But like this class, for all of you who are in biology or the health sciences, that it's useful in understanding the electrical systems of the body, but then also, like if you're marine biology and you're out in the field and you're using some electrical device, just to know, a rough idea of how it works and then how you can fix those electrical devices. So we'll get into circuits and more of that later. All right, let's have a few minutes. I'll need to stop a few minutes early to hand back your exams. But let's look at electric potential difference. The electric potential difference between 2 points is the energy per charge. In fact, it'll help you to sort of think about these things, because so far we've had electric forces, we've had electric fields, and an electric field is a force per charge, and we've had now electric potential, or we'll sometimes say electric potential difference. That's the difference in the potential between two different points, or sometimes we'll just call it voltage when we're talking about circuits. This is not a force per unit charge, but it is an energy per unit charge. So we progress from forces to fields to potential. Now also in this chapter we'll talk about potential energy, which is just the energy of a collection of particles. So we got a lot of similar things that are all floating around, and they're all very related, but if you keep this progression in your mind, it'll help you to keep them separated as we face the exam on Monday. Yeah.
Difference is the same thing as voltage.
It's similar. She asked if the electric potential difference is the same thing as voltage. And it's very, very similar. In fact, if you're talking about an electrical circuit, usually you're talking about the potential difference between 2 points on the circuit, say on the terminals of the battery. Right? So that would be potential difference. The difference in the energy per charge of 2 points in space. We'll also talk about potential as the potential just due to a single point charge, and that'll be something a little bit different. But still a measure of energy per charge. People sometimes find this difficult because it's kind of abstract, but it's also very important, as I said, for your health science and then also for your marine biology folks. It's important for you to get this idea of potential. It's an energy per charge. All right, so my delta V is the difference in the potential between 2 points, VB minus VA. We know this is point A, this is point B. The charge moves from point A to B, and so the potential difference is the difference in the potential here, which is the final spot, and this, which is the initial spot, the initial position. The units are a volt, and 1 volt we abbreviate with a capital V because it's, Voltaire, named after a person, and it's equivalent to a joule per coulomb. And of course you need to know what are the basic SI units. We've had questions like that. You might see them again. Just go with the equation. You know what a joule is. It's 1/2 mV squared. M is kilograms, V is meters per second. All right, let's see. Why don't I'm going to hand back your exams now. The way I'm going to do this is I'll just call out your names, and you can come up. But remember, you have 2 pages.